Hi everyone, Senan this side, and in this video we are going to solve this problem, which is check if array pairs are divisible by k. So before we get started with the video solution, I just wanted you guys to know that I have a PDF solution for this specific problem, which contains the intuition approach, the time and space complexity, as well as the code in C++. So if you want to download this, you can find the GitHub link in the description below so that you don't have to revisit this video again and again. So let's get on with the solution. Okay, so the problem is check if array pairs are divisible by k, and this is a LeetCode medium problem. So when I first started solving this problem, my first intuition was to generate all possible cases and then check for satisfiability. So that made me think that this is more or less LeetCode hard problem, but once you think for a moment or two, you'll find that it's not worthy of a medium level. So you are given an array of integers a r of even length n. So this is important, even length, and an integer k. We want to divide the array exactly in n by 2 pairs such that the sum of each pair is divisible by k. Okay, return true if you can find a way to do that, or false otherwise. Now we can return true if we are able to find at least one way to do that, and if not, if all the possible solutions cannot have this condition, then we return false. So if you've done a logic course, this question is more or less related to satisfiability of a given statement. Is this statement satisfiable? Given the constraints and input, is this satisfiable or not? That is the idea. And checking satisfiability is a difficult thing, and it's more or less exponential. If you try to find all possible cases and then try to figure out if there is a case that is actually satisfiable. But we are not going that route. We are trying to do, we would be doing something that is nowhere near. We are going to utilize some mathematics. We are going to utilize some modular arithmetic, which will allow us to do that in linear time, let's say. I don't want to disclose a lot of it, but yeah. Now let's look at the input, output, and the explanation. Basically the test cases. So you're given a list. So 1 2 3 4 5 6 7 8 9 and 10, and k is 5. So we need to find basically 5 pairs in this such that their sum is divisible by 5. So let's pair 1 and 9, 2 and 8, 3 and 7, 4 and 6, 10 and 5. In that way we have a pairing such that their sum is divisible by 5. So the sum is 10, 10 and 10 and 10 again. In these 4 cases the sum is 10, which is divisible by 5, and in this case sum is 15, which is again divisible by 5. Now let's look at test case 2. 1 2 3 4 and 1 2 3 4 5 6. Okay, so k is 7. So 1 and 6, 2 and 5, 3 and 4. Yeah, we can actually find a pairing, or basically 3 pairs whose sum is divisible by 7, and in this case the sum is 7 in all the pairs. Now finally, in this case 1 2 3 4 5 6, when k is 10, you can have 4 and 6, but summing the remaining elements, you cannot, making any pair, you cannot actually get k divisible by 10. So since you have 1 in this test case, you should have a 9 somewhere, right? Somewhere down the line you should have a 9, or you could even have a minus 6, not minus 6, sorry, minus 11, so that minus 11. So if you have minus 11 with sum of 1, with that you'll get minus 10, which is divisible by 10. So you see, you can have negative numbers, right? Not just positive. The test cases are positive, and if you just consider positive test cases, you might make an error, which definitely I did. And so looking at the constraints is very important. So number can be negative or positive. Number of n can be in between this, length is n, and n is even. That is very important. You have to figure this out. Let's say if this constraint was not given, if you had to check if n is even or not, and if it is not even, you return false. Although I've written that in my solution, assuming that this constraint is not there. But anyways, now let us look at the idea of how are we actually going to do this. So before, when I just started this problem, I told you that you could figure out all the possible pairs, check if it is satisfiable or not, and then return the answer if it is at some possible combination, right? But we are going to be a little smart. and we are just trying to we'll just take we'll take this statement and try to decode this statement itself, so that when you understand this problem would be a piece of cake for you. Okay, so here we are in my notebook. So this is okay, so this is the problem statement. This is, don't look at here right now. Now before we get actually with the idea, the logic, or the dry run, what I want you guys to do is, or to listen to what I'm about to say right now. So when is the sum of two numbers divisible by a number k? Let's say we have a number k, right? And we have two numbers a and b. So when is a plus b divisible by k? So when is this thing true? Now if I do this, you would realize that a modulo k plus b modulo k whole modulo is also 0. Modulo k is 0. So that means it does not exactly mean anything, but this is true, so this is also true. Basic modular arithmetic, right? So let's say if a plus, okay, let me just try to give you an intuition why this is true. So you have a number, let's say 3, right? And let's say a number 4, a and b, and you have to check modulo operation with k, which is equal to 7, let's say. So 3 modulo 7 is what? 3. 4 modulo 7 is what? 4. And the sum of this is 7, which is again modulo with 7 is 0. So basically I'm trying to do this, whereas I just do 3 plus 4 using directly a and b and taking the modulo with 7, again I would get 0. So this is true, so this is also true. The other way is to realize, if you understand this, the next step is pretty straightforward. So if a modulo k is, let's say, some so modulo operation would always result in a number 0 to k minus 1, right? A number between this range, and that is an which is an integer. So let's say this number is some, let's say k minus, or let's say this number is, let's say x. So a modulo k is x. So what would be b modulo k? This would be k minus x. Do you understand this or not? Because a plus b modulo k is 0, right? This is what we have to figure out. So the sum of integers is divisible by k. So this is the equation that we have with us. So I say a modulo k is basically x. So let's say this x plus, in place of a, let's just place x. So plus b modulo k is 0. So that means the remainder of this b should be k minus x. So if that is the case, so x plus k minus x, using this logic, x plus k minus x is actually modulo k is 0, because x cancels out. So k modulo k is actually 0. So if you hear some noise, there's some construction going on, so sorry for that. Okay, now we have this idea, so we know if a modulo, so we know that if a modulo k is x, b modulo k is k minus x, and that is the whole idea we are going to use. So let's say if we k is, let's say 7, k is 7, that means we need to find a number. Let's say if we have a number of let's say a, when doing the modulo operation with 7 you get 3, then there should exist a b for that a. When moduloed with 7 you'll get 4. So that is the idea. So this is if this is x, this is k minus x. With this, now I would like to proceed on how we are actually going to solve this problem. So what I'll do is keep a track of k elements, and which would store the number of elements that basically from 0 to k, let's say 0 1 2 dot 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 k minus 2 and k minus 1. So this array, or basically some sort of map, would keep track of number of elements which has a remainder 1 when divided by k. This would store the number of elements where when divided by the number k it leaves a remainder 2. Similarly, it leaves a remainder 3, 4, 5, 6 until the time you reach k minus 1. So now we have the number of elements which, let's me just fill some random values for this case, and let's fill this with dot dot dot. But let's say we have 10 numbers. When divided by k would give you a modulo 0, 3 here, 2 here, 2 here, 3 here, right? And let's say not 2, let's say 1 at this position. Okay, so this is your array which actually keeps track of the frequency of the elements whose remainder when divided by k gives you the index of that location. Fine. Now basically we have to make pairs, right? So if a modulo k is equal to x, then b modulo k is equal to k minus x, right? This is the idea. So if this is 1, the only elements I can pair this number with so that the sum is divisible by k is the elements which has a remainder k minus 1. So for 2, if I take this 2, the only numbers I can pair this number with, these two elements with, is with a number who has a remainder k minus 2. And similarly for 3, k minus 3, 4, k minus 4, and so on. I hope you get the idea. So now the only thing I have to do after actually placing all the values in this frequency list is to compare these two elements. If these two are same, that means I have three numbers with who has a remainder as 1 when moduloed with k, and I have three elements who has a modulo k minus 1 who has a remainder k minus 1 after modulo k. So I can pair these three elements with any of these three elements. The pairing is not exactly important. You could actually do the count of how many pairs you can actually make using some permutation combination. But if the remainder is 1, 3 elements, and remainder k minus 1, 3 elements, I can actually make a pairing for this 6 numbers. Similarly, for this 2, I need to compare it with this k minus 2. So this is 2. I have 2 elements who has a remainder 2. I have 1 element who has a remainder k minus 2. So I cannot exactly do the pairing because there would be a number remaining which I cannot actually match with any other number whose, when taken the sum, would give you the modulo k as 0 or remainder as 0. So in that case, this cannot be 1, but this should be 2 itself. And if all the pairs are matching, then that means these numbers are actually we can actually form pairs of these numbers. But now what about this 0th index, right? So when k modulo k is 0, so I said this, right? So let's say if a is, let's say k for a moment, so k modulo k is 0, and to find a b modulo k is equal to k, this cannot be true because modulo operation always results in a number 0 to k minus 1. So what I do is basically, since I have so basically the modulo, if you take the modulo again with this k, you get 0. So basically what you have to do is just check if the number of elements is even in the 0th index. If the number of elements are even, I could just divide this number into 2, and that would be the number of pairs I can actually make through this number. Okay, so now let's look at one more thing. So the sum of all the elements, if the statement is true, right? Let's assume this is true. There is a satisfiable pairing of all the elements. You try to figure this out. So we have even number of elements here, and we can actually form the pairing, right? We can form pairs. So 3 plus 3 is 6, 2 plus 2 is 4, this is 10, and so on. So that is also true because we have n as even, this n is even. So this is true. That's one more thing that you should just check this out. And now we can actually go on and discuss the solution. One more thing before we get that is in C++, when you do the modulo operation, let's say I do -1 modulo 4, you'll actually get -1. So to counter that, what I do is, let's say a number a, it could be positive or negative, either way. What I do is I do a modulo k, and again I add a value of k, and then I again take a modulo of k, right? So if a is divisible by k, so is this. So this value would be 0 if a is divisible by k. So basically using this formula, I can convert this modulo operation that works for even numbers as well. That this is just some technicality, but when you do modular arithmetic, when you perform a mod operation, you would get a number between 0 to k minus 1. So it is always a positive number, and that is something that we have to look forward to because the indexing is having positive numbers. So yep, let's now look at the code and how we actually implement this. Okay, so this bool can arrange. Before that, let's look at this private function, which is the mod. This is the modular operation I was talking about, and yep, quite straightforward. This is just because this could actually return us a negative number as well. So now what I do is I check if the array's size is even or not. If it is odd, you return false. Although it is given that n is even, so even if you remove this statement, the code would run fine. But let's say if n is not even, just for the sake of simplicity, for the sake of understanding, I'm just writing this if statement. Now what I do is I keep a track of k elements to keep the number of elements, which or basically keeping track of the remainders, number of elements which has what remainder, basically that. Now what I do is for every number in this array, I go to this arrange vector and I do the mod operation of num and k, and I increase the value. So basically I'm trying to keep count of the remainders, number of remainders that I found. And at any point, if the 0th index is odd, so that we have odd number of elements, when divided by k would result in a remainder 0. So that basically odd number of elements which are divisible by k. If we find that, we again return false because we cannot make any pairing. Now what I do is for I equal to 1 and j is equal to k minus 1, right? X and k minus x. I check if they are equal or not. If they are not equal, then return false. But if they are equal, then check all the remaining pairs, right? So I is 1, j is k minus 1. In the next iteration, I is 2, j is k minus 2. In the next iteration, I is 3, j is k minus 3. Next iteration, I is 4, j is k minus 1, and so on till I crosses j. Now there is some thing that I'm missing here, which is not exactly important, but even if you don't think about this, you would actually solve all the test cases, but you won't understand the problem or the code itself, right? The problem is correct, but the problem is with the code. For some case, I could be equal to j, right? So what do we do in that case? Because if we are doing I is equal to j, we are trying to form pairs from the same set of numbers, right? So if you understand, because if when I is equal to j, the number of elements at that location is actually even. Why? Because of this idea, because we have this even here, these are matching, so we have number of elements as even. So if I is equal to j, at that point the number that is present here, the single element that is present here, would actually be an even number because n is even. Anyways, that is not that important. I could just submit this and you would see that this is running fine. See, this beats 96.56%. If you remove this, you might even get a better this percentage. But this is not important at all. So the idea is we just keep track of the elements which has what remainder. The idea is that. Now, what is the space complexity? Space complexity is big of k elements, and the time complexity is big of n to traverse the array, and big O of k by 2 while traversing the this arrange list. I could have taken a different name, but let's go with this. So this is big O of n, and this is big O of k by 2 operations. So somewhere about big O of k itself. So that gives you the total complexity of big O of n plus big O, not big O of n plus k, and that is the worst case time complexity. So this is a linear time and linear space solution. I don't think you can actually improve more than this because you have to see every element at least once to create a pair, right? So that was the whole video, and hopefully I was able to make you understand. Anyways, the solution, the description is in the description below, the GitHub link for the PDF solution. Do check that out, and I'll see you in the next video.